Hello, everybody. I'm Dr. Shafiq, and I would like to welcome all of you in this video session. Today, we'll be talking about limit equilibrium methods to find out the stability of any slope. Okay, these are the most common, methods that we usually use to find out the stability of um, any slope. So, what is basically limit equilibrium method? The limit equilibrium method investigates the equilibrium of the soil mass tending to slide down under the influence of gravity. So basically this one try to find out the static equilibrium, means like the summation of forces in x direction, summation of y in the y direction, and summation of forces in y direction, and the summation of moment at any particular point is equal to 0. So they assume a failure surface, okay? And then they try to compare like the driving force or moment that's trying to destabilize the slope with the resistance that the soil can offer to such movement. Okay, so transitional or rotational movement is considered on an assumed potential slip surface below soil mass. So basically we assume a slip surface and then we try to find out the factor of safety, and then again we just try to assume another failure surface and try to see that in which case or which failure surface your factor of safety is minimum. Anyway, so all methods are based on comparison of forces or moments resisting instability of the mass and those causing instability. Okay, so these methods assume that the shear strength along the potential failure surface are governed by linear or nonlinear relationship between the shear strength and the normal strength. Okay, normal stress, shear strength and normal stress. So analysis provides a factor of safety defined as the ratio of the available shear resistance to the required for equilibrium. If the factor of safety is less than 1, then the slope is unstable. Okay, so two different approaches are used to satisfy the static equilibrium in limit equilibrium analysis. So you just assume a failure plane, and then you just use a single free body diagram to satisfy the equilibrium, static equilibrium equations. That's the one thing. And the second thing is procedure of slice, means like you assume a failure surface, then basically you divide that failure, like mass into several slices, and then you try to find out the factor of safety for the whole mass. Okay. Now, single free body methods. You can see here that we are assuming that the failure will occur along that line here. So the soil mass above this failure, plane. So we are talking about this total, like mass of soil. When you are using just one single body, single free body diagram, and then trying to find out the static equilibrium, then basically we call that one single free body method. So there are two different ways we can just do that one for infinite slope method and finite slope method. Okay, so let's try to explain each of them uh, so that you can solve the problem. Infinite slope analysis. So stability analysis considering infinite slope is applicable when, first of all, a slope that extends for a relatively long distance and has a consistent subsurface profile. Very important here. Okay, consistent subsurface profile for a long distance. Okay, here you can see the long distance, and for a long distance, this profile of soil is very, very consistent. That's the first thing. Second thing, what do we mean by long? Actually, the ratio of depth to failure surface to the length of failure zone is smaller than 10%, okay? So basically the ratio of that depth here with respect to the length that one will fail, if this is like less than 10%, then basically we consider that one as a infinite slope. Failure plane and seepage, if any, is parallel to the surface of the slope. So if you see any seepage here, then basically that has to be parallel to this surface here, and applies to surface revealing in granular material or slab slides in cohesive material. That can happen like both uh, cohesive or granular soil, or non-cohesive or granular soil, or cohesive or fine-grained soil. Now let's see that, let's say this is our infinite slope, and that's the line here is my failure surface, assumed failure surface. Okay. Now we have to assume several, like failure surface. But for this type of situation, when for infinite, slope, then basically you will see we don't need, like different failure surfaces here. But for all liquid, so limit equilibrium method, you will see that we need to see at least 3-4 different failure surfaces and then compare which one has the lowest factor of safety. And that's the way we try to find out the factor of safety of the slope. Now you can see here that if I take a little bit a slice here, okay, so you can see this is the weight of that soil mass. This is the normal force. This is the shear force, okay? And let's say these forces are negligible in that case. So you can see the weight of the soil mass equal to area of the soil mass multiplied by the unit weight of the soil, okay? So we are assuming the other direction, this is just 1, okay? So B into H multiplied by gamma, that's basically the weight of that soil mass. So from there, you can see your B equal to W divided by gamma H. Now, normal and tangential force component of W. So if you see that one here, this is your normal force and this is your tangential force, right? So this one is basically W cosine beta and T equal to W sine beta. Beta is the angle here, okay? Means like this angle here is beta. Okay, now available shear strength along failure, shear strength along the failure plane, we know that tau equal to sigma prime tan phi prime plus C prime. So available shear resistance, not the strength. We are talking about the total force, shear force that working along the failure plane. That's basically tau multiplied by the area of this one, okay? Now, what's the length of this one? That's basically B divided by cosine beta. Okay, B divided by, that's the length here. And the other side, it's 1. So the area is just B divided by cosine beta. Okay, so when you multiply that one with your tau, you get the total shear resistance. Okay, so tau multiplied by the area. So we know that tau equal to sigma tan phi prime plus C. When you multiply your sigma prime with A, that becomes your N. Okay, that's become your N. Plus C dot B divided by cosine beta. That's the area. Okay. Now your factor of safety is basically T is trying to push that one this way, and S is trying to resist that movement, right? So you can see when you compare that capacity divided by the driving force, that's actually your factor of safety, okay? So you just plug the value of S and plug the value of T, then basically you just get this one here. So your factor of safety would be, if you just mathematically, simplify that one, then basically you will get that one 10 phi prime divided by 10 beta plus C prime gamma H cosine square beta 10 beta. Okay. Now you have to remember that, like for granular soil, you can see your cohesion is equal to 0. So then your factor of safety would be just 10 phi prime divided by 10 beta. So what you get from this one, first of all, you can see that for granular soil, your factor of safety is independent of your height, h. There is nothing, no h here, right? The factor of safety is just tan phi prime divided by tan beta. So it's independent of the height, okay? And then what else you can see here? That your factor of safety would be 1 when phi is equal to your beta. If you see your factor of safety less than 1, this means like your phi prime is less than your beta, okay? So as long as your beta, this one is equal or higher than the phi prime, then basically you can say that this slope is stable, okay? Now let's see that what happens like if you have seepage flow working along that direction, okay? So this is basically your seepage flow. And this seepage flow is at the top of the surface here, okay? Now, weight of the soil mass is gamma sat BH. BH is the area of this one. And then the other side is 1. So that's BH. That's the total volume. If you multiply that one with gamma sat, because your water level is here, so basically you can get your total weight of the soil. From there, you can also see B equal to W divided by gamma sat into H. And again, the same way you can just do that one here, that if you take the two components of that force, one is W cosine beta and the other one is W sine beta, okay? Now, the pore water pressure at the bottom here, what would be the pore water pressure here? That's actually, you can see the height of water from here to here. That's basically H divided by cosine square beta, okay? Because this is your H. And then you can see like that distance perpendicular to that line, that's actually H divided by cosine beta. And then once you get like this one here, this line here, so this is H cosine beta, and this height is actually H cosine square beta, okay? So the force from the pore water pressure is U, is basically pore water pressure multiplied by the area. So the area here is basically B divided by cosine beta into 1, right? So this length here is actually B divided by cosine beta because this is B, okay? So you find out your force from the pore water at the bottom of the slice. Now you can see the available shear strength along the failure plane, that would be sigma prime tan phi prime plus C prime. So if you change that one, then basically this one has to be the total normal force minus the pore water pressure, no, not pressure, that's actually force from the pore water, and then tan phi prime and C prime dot B divided by cosine beta. So your factor of safety is basically the ratio of your resistance force and divided by the driving force. So if you just plug all those value what we got in the previous page and then play with that, then finally you get this is your factor of safety is equal to gamma prime. Gamma prime is basically the submerged unit weight, gamma sat minus gamma W. Tan phi prime divided by gamma sat tan beta plus C prime gamma sat H sine beta cosine beta. Now you can see here that if this is granular soil, so your C prime equal to 0, that time your factor of safety is gamma prime tan phi prime divided by gamma sat tan beta. So what it's saying again that the factor of safety of granular soil is independent again, like from the height of the slope, okay? But if this is basically cohesive soil, then basically you can see your factor of safety is a function of your age, okay? So if it is granular soil, then basically saturated condition, your factor of safety is independent of age, but the stability of the slope is reduced by gamma prime divided by gamma sat. Like this part is new here. When there is no water there, that time that was tan phi prime divided by tan beta. Now it's a factor of like submerged unit weight divided by gamma sat. Usually this one is 50%, like less when there is water there, because submerged unit weight, let's say your saturated unit weight is, let's say, 20 kilonewton per meter cube, and the gamma W is 9.8. Okay, so submerged unit weight is, let's say, 10.2 divided by 20. That's basically 50%. Okay, so if there is water, this means like actually your factor of safety will be 50% less than the same situation without water. Okay, now let's see some examples here. Okay, so this one is saying that for the infinite slope with the steady state seepage shown in the figure, determine the factor of safety against sliding along the soil rock interface. So here, okay, this interface is here. The height h that will give a factor of safety fs of 2 against sliding along the soil rock interface. So if your C equal to 0 or granular soil, then basically it's not a function of h. But here we see that this is a C-phi soil, which means like this one has cohesion as also has the angle of internal friction, 20 degrees. So basically it's a function of h. Now you can see that we already know that factor of safety is, this situation is basically the same equation what we derived here. Okay. The only difference is like this one is capital H. We derive that one based on, like lowercase h. Otherwise, this is the same equation. So your C prime is given, which is 10 kilonewton per meter square. Gamma sat is given 17.8. H here is 6 meter. Then cosine square beta. Beta is 15 degrees here. Okay, tan beta, again 15 degree. This one is your submerged unit weight, which is basically 17.8 minus 9.81. Okay, gamma sat minus gamma W. So 7.99 kilonewton per meter square. So if you solve that one, you get a factor of safety of 0.985. So what does it mean like when the factor of safety is 0.985 or 0.99? This means like this is a little bit less than 1. So the situation here looks like very unstable. Okay, so anytime this one can just slide here or already got slided. Okay, that's the first thing. Now this one is saying that what would be the height of that one if you want a factor of safety of 2. So we can use the same equation here. I can just set factor of safety equal to 2 and find out what would be the age here. Okay. So you can see here that your factor of safety is basically, you just plug whole thing here and solve for your age, and you got that 1.62 meter. Okay. So what does it mean? You can see from that equation also that your factor of safety is inversely proportional to your age. If age increase, factor of safety decrease. Okay. So if you see something like that, that you have a rock here, you better don't fill that one that much here. Okay. If you just fill that one, let's say like 1.62 meter, then your factor of safety would be 2. If you fill that one maybe like 3 meter, your factor of safety would be 1.6. I'm just assuming. Okay. So that's the way you can solve that problem. Okay. Now let's move forward. Finite slope analysis. So finite slope means like when this one is going to fail here, then we are saying that the, like the failure surface and comparing how long this one, if this is greater than 10%, then basically we call that one finite slope analysis. Okay, so you can see here that this is a circular failure surface and this is a plane failure surface. That's basically the two general shape of the potential failure surface are assumed. Okay, this one is a plane failure surface and this is a circular failure surface. So considerable evidence suggests that slope failure usually occur on curved or circular failure surface. A lot of observations, like from the actual slope failure that reveal that the failure occurs basically in a curved or circular surface, not a plane surface like this. Okay. Although the analysis like the of plane failure is suggested by Kuhlmann and provides good results only for near vertical slope. All other cases, this procedure doesn't provide good results. Okay, so that's why we are not gonna like talk a lot about that. We will just try to focus our discussion for circular failure surface. Okay. So Swedish slip circle method. This is only like when you don't make any slice, you just considering the whole thing as a single free body diagram. Okay, so that's basically the Swedish slip circle method. Sometimes we call that one like Felenius method too. Okay, this method is applicable when the slope soil is homogeneous and undrained condition. Means like clay soil, okay, and draining takes much longer period of time. In that situation, usually we use this method here. So since this is undrained condition, so your phi equal to 0 UU method we are talking about, okay? The mass of the soil above the failure surface is taken as a unit, okay, single factor of safety here. Now you can see the driving moment at O. Driving moment at O is W multiplied by L, right? If W is the weight that's working here, and the distance of the centroid of this force from this point O, vertical distance from O is L, then you can see the moment is basically W into L. And what is about the resisting moment at O? That's basically your CU, okay, CU multiplied by the distance, which is basically the radius R, okay? And then this is CU multiplied by the length of the arc, okay, length of the arc from here to here. That's the total force. Cu is the stress or shear strength, okay? And shear strength, if you multiply with the total length, then basically you will get the total force multiplied by your distance, perpendicular distance, which is actually R. So your factor of safety is basically your resisting moment divided by your driving moment, okay? So this one is basically CULR divided by WL, or CUR square phi. Phi is here basically in radian, okay, divided by W into L. So once again, try to remember which one is what. W is the weight of that single soil mass. L is the length of this one, okay? You can actually find that out, this length, from this angle here, okay? If this angle is 360 degree, then the perimeter would be 2 pi r, okay? So that's the way you can find out this length here. So although this procedure provides accurate results, but finding out the weight of this one and the centroid from this point to the centroid of this soil mass, that's actually very difficult to find out, okay? Because this is not a regular shape. So you have to find out the area or the volume and then multiply with that. But the area to find out is also very difficult to do. And definitely finding out your centroidal distance from point O is also difficult. Okay, that's why even though this method is very accurate, but usually we don't do that way. Okay, we usually try to make different slices and try to calculate that one from there. Okay, so that's the summary. Single free body methods that relatively simple and easy to use. Computations are facilitated with slope stability charts because they have a lot of charts, like provided by different scientists that we can use sometime. Both infinite slope and finite slope means like the Swedish slip circle phi equal to 0 method, that procedures fully satisfy static equilibrium conditions. Some of the method doesn't, methods don't, like satisfy that. We will just talk about that, like next part, that some of the liquid, some of the slice, method of slice, they don't use the fully, equilibrium equation. They only satisfy partially, okay? Let's say, for example, they just satisfy summation of fx equal to 0 and summation of moment equal to 0, but no summation of fy, okay? So, but these methods actually satisfy all the conditions for static equilibrium, okay? These procedures are as accurate as any other procedures when the field conditions are appropriate for their use, which means like relatively homogeneous slopes with c equal to 0 or phi equal to 0 situation, okay? And once again, I'm just telling you that finding out the weight of a single free body diagram and the centroid at which this weight is working is always difficult. So we don't use this method that much. It's just like for some hand calculation, okay? Now, procedure of slices. Procedure of slices include the following methods, a lot of methods here. So actually you can see this is your, let's say, potential failure surface, and then all the soil mass above this surface actually is have some vertical slices here, okay? I'm getting, let's say for here, I'm getting 7 slices here. So what's the advantage of this slice thing here? You can see for a small slice here, you can see this is a regular shape that you can find out the area quite easily, okay? Then you can also find out the normal force and shear force here based on the weight here, okay? And you can find out what is the centroid of each of the slide quite easily, okay? That's the reason that we usually use the procedure of slice. Now, there are some definitely complex situation here because you might have like the interslice force here, and then finding that out is could be a little difficult, okay? Now you can see here that there are several methods here. The ordinary method of slices, Bishop's methods, sometimes we call that one simplified Bishop's method, Jan Wu's method, and then you have Jan Wu's generalized method, okay? Then Low and Karafiat's method, core of engineers method, sometimes we call that one modified Swedish method, Spencer method, Bishop's rigorous method, Sharma's method, and Morgenstern-Price methods. A lot of methods there, but the thing is like hand calculation for all these methods might be very, very difficult. So we can, there are some of the easiest way, let's say for hand calculation, we usually use, let's say, ordinary method of slices or Bishop's method. We can use Jan Wu's method. We can use Corps of Engineers method. Other than that, these methods are very difficult to do with your hand calculation, okay? So I'll talk about all of these methods now. Primarily, those methods, like which we can use for hand calculation. Let's say like Bishop's method, ordinary method of slices, Bishop's method. I'll talk about also Corps of Engineers method. These are the 3 easiest method that you can do for hand calculation. Now again, the other methods, some of them cannot be done like with hand calculation, but they will be very, very easy to do that one with the finite element, like softwares, okay? So we'll talk a little bit about all the methods here. And actually when you are gonna use the software, then you have the option that which method you want to use there, okay? So there will be buttons here, like, hey, which method you want to use. So if you just click one button, then this one will just, let's say, will follow the Bishop's method, okay? Now, if it's next time you just try to say, no, I don't want to do that one. So you just go to that page and let's say you just put this button here, like Spencer's method, then this one will find out the factor of safety for Spencer method, okay? So that's the way you can just try to compare like 3 different methods and see how your factor of safety is changing, okay? And you just, when you use the software, actually the software can calculate the factor of safety of hundreds, thousands, like potential failure surface in a fraction of a minute, okay? On the other hand, if you want to do the hand calculation, then you will see that just for one potential slip surface, it might take 2-3 days. Okay, so that's why we usually do this analysis with the software, but at the same time is the requirement, okay, to show that calculation um, with, like, let's say hand computations or Excel or something like that. So you can show them that actually your software is working good, okay? Otherwise, sometimes it might be a black box that how this one is working, and the reviewer might have problem to understand that what you did there and whether this one is following the hand calculation, okay? That's why now this is kind of requirement that for at least one failure surface that is simulated in your software has to be hand calculated and show that your results are pretty close to each other, okay? Now let's talk about procedure of slice. Let's continue that one. A slow failure surface has to be predicted. I don't know actually which failure surface has the lowest factor of safety. So you just predict something here. Once you predict that one, then soil above the predicted slip surface is divided into several vertical slices, okay? So you can see we are just trying to make vertical slices here. The width of each of slice need not to be same. They can have different width, okay? Like here, I can see that there is an advantage that I make a slice just from here at that corner. Now I can assume this one as a triangle, and then this one is kind of a you know, a rectangle or rhombus. Here you can also see these are just like, you can just assume that the line here from here to here is a straight line. So what they are trying to show here, okay? The force working on each of the slices are then analyzed. So I just take each of the slices here. They have weight, they have forces, interslice forces. This is Pn and this is Pn plus 1. This is your shear force here, shear force here. And at the bottom, you can see this is your normal force. And then basically, this is your force, which is equal to your W. And then basically, you are trying to find out your NR and TR from there if you know that angle, the base angle. We call that one base angle, alpha N. Okay. Now, how many slices you need? That's a good question, right? For hand calculation, usually we do like 6 to 10 slices should be sufficient accuracy, okay? If the stratigraphy or the geometry of the subsurface is complex, more slices may be required, okay? So basically what we try to do that the bottom of the slice has, like, say, same shear strength, okay? At the same time, we want that the unit weight of soil has to be same within the slice, okay? So that I can multiply the volume of the slice with the unit weight of soil to find out the total weight of the slice, okay? So if this geometry changes, means like actually your soil is not like homogeneous or layered soil, so that at a different location, you have different, you know, like unit weight of soil as well as different, you know, like shear strength of the soil, then basically you might have to use more slices, okay? Now, for your calculation, actually, now if you have too many slices, you might need like longer period of time to solve that one, okay? The computer solutions, often 30 plus slices are used. Actually, they will just try to do that one by themselves, okay? But you have the option that you can control that how many slices you want to see. And then you just try to see, like, if you change the number of slices, whether your factor of safety changes or not. You will see that after a certain number, actually, it doesn't change that much. Okay. Now, forces and unknowns on a slice. Okay, I'm just trying to show you the free body diagram of the slice and what are the forces working on that free body diagram, because I need to solve the static equilibrium for each of that slice, and they has to be in equilibrium to make sure that this one is stable. Okay. Now, the forces here, first of all, this is the weight of the soil. Then this is your P, interslice horizontal force. Okay. Then interslice vertical force here. Now, shear force, that's working at the bottom of this one. And here is your normal force. Okay. Normal force. Now, where is the location of the normal force? That's actually your delta here. Okay. Also, the location from here to here, that where this one is actually working, where this one is working, that's the yi and yi plus 1. That's the way we just try to go move from the next slide, which would be right side would be y plus 1 and then yi plus 2. That's the way we just try to do that one. Okay. The location of the normal force delta and location of the horizontal interslice force y. Now, many cases, if we have water here, then basically you have load at the top, right? Or let's say this is the top of your slope, you might have an anchor here or other loads that you must have to consider there too. But most of the cases we can figure out or find out that force quite easily. Okay, so you can see there are a lot of unknowns here. We know the weight, we know the length from here to here, but all those things are actually unknown here. Okay, now let's see that shear force on a slice. This, you see here that actually we said that we don't know the shear force. Also, we don't know the normal force. But actually, there is a relationship between your shear force and normal force, because your tau is equal to sigma tan phi plus c. Okay, so if you know the sigma, then basically, many cases, you can find out your shear force. Okay, so that's what we are trying to see here. The tau is equal to S divided by your factor of safety. Okay, so basically I can just put that one here, that force divided by Fs. So your shear force S is equal to tau multiplied by del L. So you can just get this relationship from there, which is trying to say that shear force is known if the factor of safety and N is known. Okay, you know the soil properties, so these are known. From the slice, you can find out this one easily. Okay, from the location of the water table, you can find that one easily. So if you know your factor of safety and N, then basically you can find out your shear force. Okay, so even though we are considering this one as unknown, but basically if you know your factor of safety and N, then your shear force is not unknown anymore. Now, why we are talking about that? Okay, because we need to see that whether these slices are determinate or indeterminate structure. Okay, now you can see here what are the unknowns for N slice. Actually, let me go back here. We are just going to use this thing, but now we need to see not for one slice. We are just talking about n slice. Here we have my n is 1, 2, 3, 4, 5, 6, 7. So I have 7, n equal to 7 here, okay? Now what I don't know here, the factor of safety for this slope, that's actually one unknown. Normal force, that's n unknowns, right? 1, 2, 3, 4, 5, 6, 7. So that's n unknowns. Shear force, basically 0 unknown because I know factor of safety, and if I know my n, then basically shear force, the unknown would be 0 here. Now, location of the normal force, delta, where this one is working at the base, okay? So for n number of slices, I have n here. Now horizontal interslice force P, that's basically n minus 1. Why n minus 1? You can see for this one here, actually you have interslice force this way, but you don't have anything here, okay? This one will be balanced by actually the normal force and shear force here. So you have one less here and one less here. So you have one force here, 2, 3, 4, 5, 6. So for 7, like total slices, I have 6 unknown horizontal force. That's why this one is n minus 1. Similarly, I have the vertical interslices force is n minus 1 because 1 would be less because here and here you don't have any vertical interslice force. That vertical force here is actually n, okay? Here is n. Now location of the interslice force, that's also if we have n minus 1 force, then basically the location of n minus force is basically n minus 1. So total unknowns is 5n minus 2, okay? Now let's compare that one, how many equations we know for like n number of slices, okay? So you can see here the summation of equilibrium equation is summation of fx equal to 0. For n slices, you have a number of equation. For each of the slices, your summation of fy equal to 0, so totally you have n. Then summation of a moment, you have n. So total number of equation, you have 3n, okay? Total number unknown is 5n minus 2. So your number of equation is less than your number of unknowns. That's why the problems, all the problems is statically indeterminate. Okay, statically you cannot solve them with this number of equation, like that many unknowns here. So now what we can do, we just assume some assumption and try to find out like, hey, how we can minimize that one so that the number of equation would be equal to the number of unknown. If we can, that's basically all that methods, like with all kind of like methods we are talking about. This is coming from what assumption you are taking to simplify that one so that this one could be statically determinate, okay? Some of the methods you can do that one with your hand, but some of the method would be really difficult to do that one by hand calculation because that requires iteration, for your calculation, and hand calculation will take extremely long time to do that, okay? So that's why basically the finite element method, like after the invention of computer and all kind of, codes, basically now we can solve that one much easily using the numerical method, okay? Now let's see how we can minimize these unknowns. That depends on what kind of assumption you are using. Now, first one here, the most common one actually using all methods, that's the location of the normal force N, okay? it is reasonable to assume that the normal force N acts at the midpoint of the base of the slice. Okay, so your delta is basically del L by 2. Okay, the midpoint here. This assumption has a very little influence on the computed factor of safety. Okay, they check that one, like if they move that one a little bit this way or this way and then keep that one here, then basically doesn't have that much significant effect on your factor of safety. Okay, thus we can eliminate the location of the normal force delta from the unknowns. Okay, so you can see here we had location of interslices force that was n minus 1. So when we recalculate that one, then basically we get 4n minus 2. Okay, so location of this one has to be actually 0 now. I made a mistake here. That is 0. So if we add, oh no, this is location of interslice force. Yeah, that's fine. This is n minus 1. Actually, the location of delta, we already take that one out. So if we add them, you can see n plus n plus n plus n. You have 4n minus 2, because this is positive, this is negative, cancels out. So 4n minus 2. But what you see here, that the total number of unknown is 4n minus 2 and total number of equation is 3n. So the problem is still statically indeterminate. Okay, so further assumptions are needed. So based on that further assumptions, actually, we all that methods are there. Okay, that how they are trying to calculate each of that, how they are trying to simplify that one to make that one statically determinate. Okay, now let's see assumption for all methods. Okay, so you can see here for limit equilibrium solution, all method of slices. Actually, this is for slices, more assumption about the forces acting on the slide are needed. Okay, some methods satisfy complete static equilibrium, others satisfy only some of the requirement for the static equilibrium. Okay, so it's very difficult to make sure that I have the same number of equation and same number of unknown. Many cases when you assume anything, then we basically see that they may not, okay, satisfy all the equations, all the three equations. What is that three equations? Summation of forces in x direction, summation of forces in y direction, and summation of moment equal to 0, right? So you will see that some of the method doesn't actually satisfy all that static equilibrium equations. So you can see here, for example, Bishop's method assumes that the interslice forces are horizontal. Okay, when you know this is horizontal, then basically there is no interslice force in the vertical direction. Okay, because it's just in the horizontal direction. Okay, so what he is trying to do, that he is just trying to solve only summation of Fy equal to 0 and summation of moment for the global, the overall, like slope, that's actually 1. So basically you have total number of equation n equal to 1. Okay, he's assuming that this one is force, interslice force is actually vertical. This means like, and then he is not actually satisfying that the horizontal forces is equal to 0. So basically he is ignoring any interslice force. Okay, so total number of unknown is basically the factor of safety and then the normal force, which is for n number of slices, you have just n. So total unknowns is just n plus 1, and total number of equation he is using n plus 1. Thus the Bishop's method doesn't satisfy the summation of fx equal to 0. Okay, So even though he is assuming that the interslice forces are horizontal and then he is not summing them up, what does it mean? Basically, there is no interslice force, okay? So you can see here, if you go back here, then basically this one is 0, this one is 0, and location of interslice force is 0. Okay, so you have only unknown is your factor of safety and the normal force. Okay, that's n+1. That's what he is doing here. So I'm just showing that as an example. But then you would see that each of that method is actually using some simplification and then basically not using all that. There are some methods though, like Spencer's method and Morgenstern, Sarma's method. They are using like all the three equations and satisfying all the three static equilibrium equations. But some of the method don't, okay? Now, equilibrium condition that's satisfied by limit equilibrium method. You can see this is each of that method. I wrote it down, and this is the summation of fx, summation of fi, fy, and this is your moment equilibrium. So ordinary method of slice, they only do the moment calculation. No xy doesn't satisfy the summation of fx equal to 0 and summation of fy equal to 0. Bishop simplified method, as I said, like in the earlier, actually the last slide, you can see they do the summation of fx and then not summation of fy. Actually, this one is a little bit off here. This one has to be that this one is no and this one is yes and this one is yes. Okay. Similarly, you can see these three methods don't do the moment equilibrium. So Spencer's method, Bishop's rigorous method, okay, then Sharma's method and Morgenstern-Price method. These are the four methods. They satisfy all the three equations, okay? So basically that's why they're usually more accurate, but very difficult to do that one with hand calculation, okay? Now let's start with ordinary method of slice. So what's the assumption? The assumption is saying that ignore interslice force, okay? So if you ignore all the interslice force here, and if you know that angle here, then basically it's also assumed that your normal force N equal to W cosine alpha, okay? This one is relatively simple, good for hand calculation, okay? It is relatively accurate. The errors are on the conservative side, underestimates factor of safety when error occurs, okay? Even if you have any error there, you are still in the conservative side. Means like your factor of safety, you are getting less, okay? So basically, in practical field, this one is not going to fail, okay? Then gives exact solution for phi equal to 0, only applicable for circular slip surfaces. Okay, so these are the assumption here and how this one will work. Now let's take a look at how we can calculate that one here. So first of all, equilibrium condition satisfied by the ordinary method of slice. You can see you are not trying to find out the summation of forces in X or Y direction. You are just only trying to find out the moment, okay? How much is the resisting moment and how much is your driving moment. Once you get that one, your factor of safety is your MR, means like resisting moment divided by driving moment, okay? That's the only thing you are trying to do here. So since you assume your normal force is a function of your weight, and you know the weight of each of the slices, so basically this is no longer unknown here. And since you are ignoring all those things, so basically you have just one unknown, and you have just number of equation. One means like you are only satisfying the global, like moment at a certain point, okay? Thus, the ordinary method of slides do not satisfy force equilibrium equations like summation of fx equal to 0 and summation of fy equal to 0, only take the moment, okay? Now I'm gonna show you that what does it mean actually, okay, in the next slide. So here you can see this is your assumed slip surface, okay? So here is like, let's say, we already did that one, sort of when we were talking about just one, like single, um, single free body diagram. Now we don't have single free body diagram. Now we have several slices here, okay? Now you can see this is one of that slices here. So you know the weight of this one here. If you know the distance, perpendicular distance from O to that weight here, which is basically R sine alpha n. Alpha n is the angle here, okay? This angle is alpha n here. So this is your R sine alpha because this is R. So the distance is R sine alpha. So the driving moment is W multiplied by R sine alpha, okay? Driving moment is W divided by R sine alpha. Now, you can see your NR is also assuming that has to be W cosine alpha because they are not considering any other force in that direction. So it's obvious that this one has to be, like NR has to be W cosine alpha, and your TR equal to W sine alpha. So your shear resistance here, TR, that's basically is tau multiplied by the distance from here to here, which is delta Ln. So tau into delta Ln. Now you can just put the values here because you know that tau equal to sigma tan phi prime plus c prime. Once you multiply that one with the area, okay? So the area is delta Ln multiplied by 1 in the other side, okay? So you get, this is your TR from there, okay? So what would be your resisting moment then? That would be this force multiplied by your R, okay? So this one is trying to rotate this way, and the force along that line is trying to resist that movement, okay? So that would be like that shear force along that line multiplied by the distance from here to here, which is actually R. So that's your resisting moment. So your factor of safety is basically W cosine alpha tan phi prime plus C prime B divided by cosine alpha. That's basically your del Ln, okay? Del Ln, the B is the width of this slice here, okay? You can just measure because you just make your own slice. So you can measure what is your B here. And then that should be equal, should be divided by the summation of resisting, or driving moment, okay? So each case is actually R and R cancels. So you don't see that R here. So you just see this part here and W sine alpha at the bottom. So you have like, let's say here, like let's say 1, 2, 3, 4, 5, 6, 7, 8 slices. So you have to just add all of them together. So basically what we do in Excel, for each of the slice, we just calculate like this thing, because for each of the slice, your alpha is going to change. Okay, your weight is going to change. And phi prime, this one is same. C prime is same for all slices because they have like homogeneous, like soil mass here. Then you can just find out the factor of safety quite easily. Now here, this is one of the example for ordinary method of slice. You can see they are trying to solve that one here for the slope shown below. Find the factor of safety against sliding the trial slip surface shown. Use the ordinary method of slice. So basically, that's given here. And for this particular case, they gave you the failure surface. In practical situation, actually, you have to pick up a failure surface. Okay. Now, the property of the soil is given, which is, let's say, gamma equal to 19 kilonewton per meter cube, phi equal to 20 degree, and C prime is 20 kilonewton per meter square. So first of all, we just try to make that one several, like slices here. I can see they have like 9 slices here. Okay. Now, usually we do that one these days. Like in the past, they used to use like graph paper to put the whole thing there. Now, you can do that one in AutoCAD, okay? So that you can know like the distance from here to here. You can find out the distance from here to here. You can find out what would be your B, okay? Because this one has that function, okay? At the same time, what we assume that this one is from here to here is a straight line, and you can find out the angle here. Usually at the middle, we try to get because the angle here and angle here is changing. So we take the angle at the middle, and that will be your alpha here, because this angle is extremely important here. You can see this is your alpha here, okay? So we are trying to find out that alpha here because these properties are given, okay? So you have to find out B, you have to find out the length here and here so that you can find out the area. Okay, so for this particular slice, let's say what would be the volume of this slice? That would be this plus this divided by 2 multiplied by this. Okay, so that would be the total area. In the other side, it's 1, so the area and volume is basically same. So if you know the unit weight of soil, then basically you know the W from here. Okay, and if you know the alpha here, then basically you know that what would be the distance from here to here, which is basically the sine alpha, okay, our sine alpha. Now let's move forward. Now the sliding wedge is divided into 9 slices. The weight of each slice is just calculated like this. We usually do that one in Excel. Okay, I'll just show that table next to you. So you can see, just for example here, that you can see if you try to find out the weight here, then let's say for this one, what would be the weight? That would be this plus this divided by 2 multiplied by 2.09. Okay, so you can see 2.84 plus 6.12 divided by 2 multiplied by 2.09. And then this is basically the unit weight of soil. So you get 177.9, okay? Then if you think about this one, that this one has to be this plus this divided by 2 into this multiplied by your unit weight, okay? For this one is a triangle, okay? So this one has to be half into 2.84 into 0.6, right? The area of a triangle is half into this, right? That's what they're trying to do. Half into 2.84 into 0.6 multiplied by the unit weight So this is basically your, that many kilonewton is the weight of that thing, okay? Now, one other thing is like sometimes it's very difficult to find out your alpha n here. So what they're trying to do, this is the midpoint of each of the slices here, and they are just trying to draw a line here and finding out this angle from here. That's actually the same angle here, horizontal with this line here, okay? But this one is easier because you can just draw that line at the midpoint here and then go there and try to see what is the vertical angle that makes here, okay? So again, this one would be much easier to do that one in AutoCAD, like if you know how to do that. If you don't know, as a civil engineer, I expect that all of you already know that one. Now, if you don't have that one, then basically you can just draw that one on a graph and then measure that angle with it, with any, like protractor or something like that. Okay, so you can just find out these angles here. Now here is basically, you can do that one in your Excel. This is your slice number. You already know the weight of this one. You already measured the alpha n from there. Then basically you do some simple calculation here to solve that equation, like sine alpha n, cosine alpha n. You just try to find out your del ln, which is nothing but b divided by cosine alpha. Okay, so that's basically this line here. Then you find out your w cosine alpha n and w cosine alpha sine and cosine. Then basically you just try to find out, plug that one in that equation and find out your factor of safety. Okay, now let's see here. So that's basically your equation. You only need like w cosine alpha and w sine alpha. All other values are given. Okay, so that's what you are trying to do here. Okay, that's the equation you are just trying to use here. Okay, and finding out your factor of safety from there. So that's the way usually we do that one. This is not that difficult at all. Only thing is a little difficult to find out this information. Okay, these two informations from for each of the slice. So there is two different methods. Okay, in the past they used to draw the whole thing in a graph paper. Okay, and then you just try to find out each of them just using your geometry box, that what is the length, okay, measure that one, and what is your width and what angle this one makes. So if you have a graph paper and a geometry box, you can just do that one using that one. But if you, these days actually people use that one for AutoCAD drawing, because that's much more accurate, than the graph system. Okay, so I'll just like encourage all of you to use that one. This one would be our first. I just assigned you like a homework number 3, where I ask you to do a problem with ordinary method of slice, and you might have to like use AutoCAD to do that one. Okay, so that's basically for today. If you have any question, please don't hesitate to come to the Zoom session. We can definitely discuss about more about that. I know this is not that easy thing, like this one is a little bit easier, but in future we are going like a little bit more difficult. Okay, so if you have any question, please don't hesitate to contact me. Thank you so much for your attention.